Cables under a distributed load are cables with a load that is pulling down from the cable evenly throughout the whole cable. And sometimes that load is going to be constant throughout the whole thing, and sometimes it can be varied. But that is why we have these equations to solve for that. If you have a cable that is under a constant load and it is symmetric, so the two ends are at the same height, you can use these equations because they're symmetric, and it turns out to be simpler to solve. So a few of the variables that are here we have are W naught, which is the weight per unit length of the load on the cable. We have our L, which is the distance between supports. We have H, which is the sag between the height of the support and where the lowest point on the cable comes down to. We have T max, which is the maximum tension that occurs in the cable, which is going to occur at the point where the slope is the greatest in the cable. So that's almost always going to be at the ends, at the reaction places. Then we have the T sub H, which is the horizontal tension, which for any cable problem is going to be the same throughout the length of the cable. So the horizontal tension is going to be the same throughout, and where the slope is 0, the horizontal tension is going to be the only tension, which means that that is going to be the minimum tension. So if you're asked for the minimum tension, that is going to be wherever your horizontal tension occurs, or where the slope of your cable is 0. Then you have the curve of the cable. That gives you the parabolic shape. So distributed loads on cables create a parabolic shape in the cable, unlike catenary loads, which creates a hyperbolic shape. But we'll get into that with another video. And then the length of the cable is used by this more complicated equation, but all of these come from this equation here, which is which gives you the curve of the cable given a loading function and the horizontal tension in the curve. And so, like you can see, that's a double integral. It can get pretty nasty when it's not a nice symmetric load like this, and you can use these equations. And then there's a couple other loads that are a couple other equations that help you get find other variables you need, such as the horizontal tension. So that horizontal tension in other textbooks or videos might write it out differently. I've seen it written out as T naught and also F sub H, which is horizontal force, and I use T sub H because horizontal tension makes sense. So if you want a video going over an example problem with something a little bit more complicated than just a symmetric load, you can click on this video link and that'll take you there. I've also gotten the steps written out down in the description for you to check out. Also down in the description, I've got some links to Teespring and Amazon where you can buy some merch by Student Engineering, and buying that helps me out a lot. So if you're new to this channel, my name is Preston Palmer with Student Engineering, and my goal is to help other engineering students like me better understand engineering. So if you found this video helpful, hit that like button and please subscribe.